Hello all, welcome back to the second video for section 1.1. The first thing we want to talk about is some notation. So we introduce matrix notation for the sake of convenience and efficiency. So given a linear system like the one we have below, one of the things we can do for convenience again, is just to record what coefficients appear in each variable. So we got a 1 for x1 and a 2 for x2 and make it -1. And similarly for the second equation, we've got 1, 1, 1. And for the final one, -2, -3, and 3. And for, this is the coefficient matrix. It's just recording the coefficients of our variables. You might reasonably ask, well, what about the constant terms on the right-hand side? That's for our augmented matrix. So similarly, we could record all of the coefficients of our variables along with the constant terms to get our augmented matrix. And as long as we are consistent with what order everything comes in, there's no loss of information here from passing from the set of 3 equations to just this matrix of 12 numbers. All right, so the size of a matrix is the number of rows and columns it has. So this example we just saw is a 3x4 matrix. We always count number of rows, number of columns. And the way I remember this is by going down and over the spell that traces out an L. If you go across and down, that doesn't trace out an L. L for linear algebra, of course. So that's how I keep it in mind. So other examples, just to make sure we're on the same page. If we have the matrix 1, 0, 2, 1, 3, 5, this is a 3x2 matrix. Not 2x3. Okay, and that's it for notation. This is we're going to use the matrix notation in the entire term. All right. So the next thing to talk about is our first stab at solving a linear system. So given a linear system, its solution set is the collection of all possible solutions for our for the linear system. So again, up here we might have a bunch of different values for x1, x2, and x3 that we could plug in and make all 3 of these equations true. So if we collect them all together, that's just the solution set for our linear system. When we say that 2 linear systems are equivalent if they have the same solution set. And so anytime we're trying to solve a linear system, our goal is to replace the given linear system with one that's equivalent, whose solution set is easier, at least easier to determine. So recall last video, we solved the linear system x1 minus x2 is 3 and 2x1 plus 3x2 is equal to 1. Let's look at the process. Let's look at this process and then write down the sort of sequence of in between linear systems, intermediate linear systems that we use to eventually get the solution. So the first thing we did was take our linear system. It looks like we multiplied that first equation by -2 and then added it to the third row to get 5y is equal to -5. So the first thing we do up here is we take our original linear system. We haven't changed the first equation, but we replace the second equation by equation 2 minus twice the first equation. So we've got no x1s. We have got 3 times -2 times -1, so +2, that's 5x2, and then 1 minus 2 times 3 is -5. And you can check these 2 linear systems are equivalent. They do have the same solution set. The next thing we did, once we had 5y is equal to -5, well, we can divide both sides by this equation to get y is equal to -1. So the next equivalent linear system that we have didn't have us changing that first equation at all. It just had us dividing both sides here by 5. So this is x2 is equal to -1. And then finally, I mean, here I think we plugged in the value for y into our original equation, but the same thing we could do. Effectively, the same thing happens is if let's move this up for a sec. Oh, there we go. So yeah, what did we do here? So we replaced row 2 by row 2 minus 2 times row 1. And here we just multiplied row 2 by 1/5. The last thing we want to do is replace row 1 by row 1 plus row 2, because if we add these two together, the negative x2 and the x2 here are going to cancel, and you'll see what happens. We've got x1, x1 plus no x1 is just x1, minus x2 plus x2 is 0, and 3 minus -1 is 2. We don't change that second. So here we replaced row 1 by row 1 plus row 2. Okay, and now we still have a linear system technically, but it's so simple that we can just read off what its solution set has to be. The only solution is x1 is 2 and x2 is -1. And you can check that both of these intermediate linear systems have the same solution set. Good. Okay, so then more generally, what's happening is every time we're faced with solving a linear system, we want to perform one of 3 elementary row operations. So these are operations that you can perform on a linear system without changing its solution set. Or in other words, operations you can perform to produce an equivalent linear system. So the first one that we saw was we're always allowed to replace one row or one equation by the sum of itself and a multiple of another row. So replace one row by the sum of itself and a multiple of another row. So that we did several times right here. Oops. So our first step was to add -2 times row 1 to row 3, and that killed off that x1 in the second equation. So what else can we do? We're allowed to interchange rows, and this one we didn't actually use, but we can interchange rows, any 2 rows. And surely that doesn't change the solution set. And then finally, we're allowed to multiply all entries of a row by some non-zero constant. Multiply all entries of a row by a non-zero constant. Okay, and those are our elementary row operations. Right, and our goal is always a system where each variable is only appears once. So that's what we did up here, and that's what we'll always be trying to do. Okay, so as an example, let's solve the linear system that we opened the video with. All right, so then let's get our augmented matrix first, because it'll be less clunky carrying around all of these equations. So our augmented matrix means that we just carry all of the numbers in a matrix, and we can put down the adding and the names of the variables, since that'll all be implied. Okay, so we've got 1, 2, -1, -3. We've got 1, 1, 1, 4, -2, -3, 3, and 8. Okay. And so we want only one mention of x1. So let's use this x1 to cancel out or to eliminate the other mentions of x1. Or in other words, we'll use the 1 here to eliminate the numbers below it, or the numbers in the same column as it. So let's, yeah, we'll write that down. So we'll use the 1 in row 1, column 1 to eliminate everything in the same column. Everything else in that column. Okay, so if we want to eliminate the 1 beneath it, we should just take row 2 and subtract row 1 from it. So yeah, we'll replace row 2 by row 2 minus row 1. Or if you prefer, row 2 plus -1 times row 1. Okay, so we're gonna get what? Our first row hasn't changed at all. Our second row is going to be 1 minus 1, that's 0. 1 minus 2 is -1. 1 minus -1 is 2. 4 minus -3 is 7. And our third row hasn't changed either. Okay, and just in case, just to make sure we're all on the same page as what's happened with our linear system, we could understand this as a linear system always, right? This is just the linear system. x1 plus 2x2 minus x3 is equal to -3. We've got no x1, so we've just got minus x2 plus 2x3 is 7. And then minus 2x1 minus 3x2 plus 3x3 is equal to 8. And yeah, since we've used only our elementary row operations, we know that this linear system has the same solution set as the one we started with. Okay, let's do the same thing for row 3. So we want to replace row 3, oops, by, well, let's see. If we want to kill that -2 with that 1, we'd better add 2 times row 1 to it. So row 3 plus 2 times row 1, right? Because that's going to be the thing that kills that lets this 1 cancel that -2. All right, so what is our resulting matrix going to be? Row 1 hasn't changed. Row 2 hasn't changed. Just row 3. So we've got -2 plus 2 times 1 is 0. We've got -3 plus 2 times 2 is 1. We've got 3 plus 2 times -1 is also 1. And we've got 8 plus 2 times -3 is 8 minus 6 is 2. Okay, or if you like, the corresponding linear system is x1 plus 2x2 minus x3 is -3. Now we've got minus x2 plus 2x3 is 7. Here we've got x2 plus x3 is 2. And notice that we've succeeded in eliminating every other mention of x1, every other instance of x1. So yeah, this is always what we're headed towards. We want 1 appearance of each variable, and that'll eventually give us just a whole solution. Okay, so I'm not going to keep on writing down the corresponding linear systems. I think you've seen that enough times to sort it out yourself. So let's just wrangle these matrices to find a solution. So let's now, okay, so now we should choose a candidate for being our x2, and the other ones we should try and eliminate. So what are we going to do? Let's maybe keep, what have I decided to do over here? Yeah, let's use the -1 x2 in row 2 and eliminate everything else in that column. So we'll use row 2 to eliminate everything else in column 2. Okay, so let's maybe replace row 1 with what do we need? With row 1 plus, looks like 2 times row 2. Oops, 2 times row 2. Because if we do row 1 plus 2 times -1, that's going to be 0. Good. Okay, so let's see what happens. So now 1 plus 2 times 0 is still 1. So that 0 isn't going to affect the one that we wanted to keep. 2 plus 2 times -1 is 0. Now we've got -1 plus 2 times 2 is -1 plus 4 is 3. And then we've got -3 plus 2 times 7 is -3 plus 14 is 11. And now row 2 and 3 haven't changed. So 0, -1, 2, 7, 0, 1, 1, and 2. Okay, now let's replace row 3 by row 3 plus row 2. So now our first row hasn't changed. Our second row hasn't changed. Our third row becomes, well, 0 plus 0 is 0, fine. -1 plus 1 is 0. 2 plus 1 is 3. 7 plus 2 is 9. Okay, and now we've done what we wanted to do. We chose this one arbitrarily. All we need to do is, yeah, we could have chosen the 1 in row 3. Either is fine. Either will work. We can't choose the 2 in row 1 because we already chose. Yeah, if we do that, if we start adding this around, then we'll get rid of those zeros. So once you've fixed an x1 here to solve for, you must look at the rest of the matrix for your choice of x2. Yeah, we'll get an algorithm for this in 1.2. So don't sweat that part just yet. Okay, so now we do want a 1 here, so we know that it's x2 is equal to some number. So let's replace row 2 by -1 times row 2, and now we're going to get proper matrix here. 1, 0, 3, 11, 0, 1, -2, -7, 0, 0, 3, 9. So now finally comes. We can isolate the this 3 for our x3 and use it to eliminate everything else in column 3. And maybe let's first replace, for ease of algebra, replace row 3 by 1/3 of row 3. I think that'll be easier for us later on. 0, 1, -2, -7. 0, 0, 1, 3. Okay. So if we do what? Take out row 2 and replace it with row 2 plus 2 row 3. What's going to happen? Our row 1 hasn't changed at all. Our row 2, what's happening? -2 plus 2 is 0. -7 plus 6 is -1. And now we've got 0, 0, 1, and 3. And we're almost finished now. If we just get rid of that 3, then we're all set. So let's replace row 1 and take it to row 1 plus, what's going to do? -3 times row 3. That should do it for us. 1, 0, 0. And what have we done here? 11 minus 3 times 3 is 2. 0, 1, 0, -1, 0, 0, 1, and 3. And notice that now the corresponding system is so simple. It's hardly a system. x1 plus no x2 plus no x3 is 2. No x1 plus x2 plus no x3 is -1, and x3 is just 3. So it's hardly a system, it's just a list of our solution for our linear system. Okay, I'll see you next time with another video.